Greetings, students. Mr. Keister here again with you today as we continue on in our e-learning, and we are moving ever closer to the semester. So the board behind me are juveniles. These are Chem 2. Had we originally been time, this is actually would have happened on the 28th. We were in Chem 2. I think we're 3 or so days behind that. But regardless, remember that we are following our modified analysis on daily basis. I do update it, and so make sure that you are doing that. And take our notes. We are finally in the very last unit of our course this year. This is Unit 12.2 on chemical equilibrium. Equilibrium has a lot to do with rates and reaction rates and rate laws, which we studied in Unit 12.1. So this is very much associated and connected to that. Before we continue or begin with this unit, I want to make sure that you are aware of something. And this goes for both Chem 2 and Honors Chem. I have a fairly good idea of how far we're going to get in this unit, based on the number of days we lost, of course, due to this pandemic, number of school days we lost, as well as our abbreviated schedule for e-learning based on what the administration set out for us. So having said that, whether or not we get to some, all, or none, and all three of those are possible, of this particular unit, Unit 12.2, I am going to go ahead and record all the lectures, just as if we had all been in class for all of this Unit 12.2. And whether we get to them or not, they are going to be posted on my webpage, as all the other video lessons are, for you to be able to view and see. And I want to make a very important point here. And again, whether we do or we don't get through any or all of none of these lessons, this unit on equilibrium is an extremely important unit in finishing up the year in either of these courses, Chem 2 or Honors. I can tell you this with 100% certainty. If you're in Honors and you go on to either AP Chem or you go straight to your first general chemistry course in college, you are absolutely going to have to know and be familiar with and been exposed to chemical equilibrium. It is going to come up. It is going to be taught. It is going to be gone through in even greater detail than what I can here, based on the amount of time we have. In other words, you are absolutely going to see it again. You are absolutely going to be responsible for knowing it. Let me also echo that sentiment for you guys in Chem 2. Now, I realize most of you are juniors or seniors, and so your college chemistry classes are much closer at hand. I will say the same thing to you. Chemical equilibrium is a topic in general chemistry in college that is going to be covered without a doubt. Okay, so bottom line for all of my students is this. Like I said, the video lectures, the assignments, the labs, all that stuff, I'm going to present, and they're going to be available to you on Canvas. I do not know how long you have access to my Canvas course once school lets out for the year. And of course, we now know that our last day is May the 15th. So having said that, you need to take it upon yourselves to have these videos uploaded somewhere else. In other words, take them off my Canvas course, take the assignments off my Canvas course, and put them somewhere else where you have access to them later. Because I know at some point in time, you are going to be shut out of my course in Canvas once the school year ends. I don't know when that is. I'm not a tech person. But I know that you will be shut out from them. So while I'm saying this, while I'm thinking about it, keep this in mind that you want to have access to this material. So there you have it. Okay, so we're going to start now with Unit 12.2, Chemical Equilibrium. The condition in which the concentrations of all reactants and products in a closed system cease to change with time is called chemical equilibrium. For equilibrium to occur, neither reactants nor products can escape from the system. This is what a closed system is. When you want to run a reaction in a test tube or an Erlenmeyer flask or a beaker or whatever, that is not a closed system. That is an open system. In other words, once you run the reaction, if, for instance, if one of your products is a gas, or if any of your reactants are gases, they can escape out the top of the container and go into the surroundings. Energy can be lost from the container or be taken in to the container from the surroundings. That is not a closed system. All right. A closed system is exactly what it says it is. It's closed, meaning this reaction is going to be run in a sealed container, whereby once you put the reactants in there, nothing else is getting in and nothing is getting out. And that includes energy as well. Okay, so that's what a closed system is. It's the only type of system where equilibrium can occur. Chemical equilibrium occurs when opposing reactions are proceeding at equal rates. All right, so here's where rates come in. The rate at which the products are formed from the reactants equals the rate at which the reactants are reformed from the products. Here again, this cannot happen in an open system. All right, once reactants form products, that's it. But in a closed system, all right, once reactants are form the products, there's nothing preventing the products from going the opposite direction and reforming the original reactants. Again, that can only happen in a closed system, not an open one. So if we take a general reaction where reactant A forms product B, its reverse reaction then would be B then reforming A. And the rates of these two reactions would be. So here we go with our rate law. All right. So for the forward reaction where A forms B, remember rate is equal to a rate constant K times the concentration of the reactants. Here A is the reactant. It's our only reactant. So the rate equals K times concentration of A. I put an F there, a subscript F next to the K to show that that's the rate constant in the forward reaction. For the reverse reaction, since we're in a closed system, it can happen too. Now B becomes the reactant, all right, and it reforms A. So the rate law for that reaction is rate equals K times concentration of B, because now B is our reactant if we're looking at it from the opposite direction. And again, I labeled this K with a subscript R to show that it's the rate constant of the reverse reaction. So if we start out with pure A in a container, seal the container, closed system, and it then begins to react to form B, then the concentration of A starts to decrease and the concentration of B starts to increase. We talked about this at length in Unit 12.1 on reaction rates. Recall rate of disappearance. Remember, as time goes on, reacts disappear. All right, their concentrations decrease and products appear. So we have a rate of disappearance of A, a rate of appearance of B. Eventually, the reaction reaches a point at which the forward and reverse reaction rates now are the same. And compounds A and B are then said to be in equilibrium. All right. So let me advance this up. the rate, all right, the rate of the forward reaction and the rate of the reverse reaction are equal, all right? So if those rates are equal, then we can say then that the rate laws, all right, the rate laws for those two reactions are also equal, all right? So here's the rate of the forward reaction. Rate equals K, K of the forward reaction times concentration of A equals the rate constant of the reverse reaction times the concentration of B. All we have done is set these equal to one another. Then we're going to do a little rearranging algebraically. We're going to express the ratio of our original product B, concentration of B, to our original reactant A. All right, so we basically divide both sides by concentration of A, which then takes that away, and that goes under there. And then we did the same thing. We isolated the concentrations on one side, the rate constants on the other, all right? And so by doing that, we divided both sides by the rate constant for the reverse reaction, and now we have the concentration of B over the concentration of A, or the ratio of those two, is equal to the ratio of the rate constant of the forward reaction over the rate constant of the reverse. And that right there is equal to what we call the equilibrium constant. Notice the equilibrium constant has a capital letter K, not a lowercase letter, as a rate constant does. So this is the relationship between rate constants and an equilibrium constant. The equilibrium constant is the ratio of the forward rate constant compared to the reverse rate constant. So Kf over KR, K forward over K reverse is equal to K, which is called equilibrium constant. And in general, we call that Kc or KEQ. You'll see both of those in your literature, in your textbooks and so forth. Normally, of course, KEQ makes sense, equilibrium constant. Normally, you tend to see Kc a little more often, but they both mean exactly the same thing. All right, they mean exactly the same thing. All right, let's go to the next page. So thus, at equilibrium, the ratio of the concentrations of A and B equals a constant, all right, equals a constant. Equilibrium is dynamic, all right, it's dynamic. There we go. Meaning that once equilibrium is reached, the reaction does not stop. This is a common misconception about equilibrium, that once the rates of the two reactions are the same, reaction's over, all right? Well, in an open system, that's true. Once the reaction's gone to completion, it is over. We talked about that many times when the reactants run out or the limiting reactant runs out. However, in a closed system, the thing just keeps going. Reactants form products, products reform reactants. But when those rates are the same, that is when the system is at equilibrium. So again, equilibrium does not mean that once it's achieved, the reaction stops. Instead, it means that the forward and the reverse reactions are occurring at the same rate of speed. Okay? Make sure you understand. Okay, let's talk a little more specifically about Kc or KEQ, the general equilibrium constant. In 1864, based on their work with reactions involving equilibrium systems, Cato Goldberg and Peter Vaj theorized what is called the law of mass action, which expresses the relationship between the concentrations of the reactants and products at equilibrium for any general reaction. All right? So if we have a reaction here we're showing a double replacement, but it doesn't have to be. For the general reaction, A plus B, notice here we have this now. We have the double arrow. This means that the reaction occurs in both directions simultaneously, again, meaning we're in a closed system. Yielding P plus Q, with the lowercase letter representing the mole coefficients. All right. The equilibrium condition is expressed by this: Kc or Keq is equal to the concentration of our products. Here we have two products. The concentration of P times the concentration of Q raised to the power of their mole coefficient. That's very important. Okay. Of course, if this was a 1, then that would be a 1 as well, and we wouldn't need it. But anyway, that's what it means. Over the concentration of the reactants. All right. So it's products over reactants. All right. So any K, and there are many, by the way, K is equal to the products over the reactants. Sometimes we use concentrations, sometimes we use pressures. We'll talk about all that here in just a little bit. This is in general, all right? This is in general. So it's products over reactants. Again, the general K, Kc or Keq, uses concentration, all right? And again, make sure that these are raised to the power of your mole ratio number, all right? Again, note, you'll also see Keq in some textbooks rather than Kc. Same thing, all right? This relationship here, law of mass action, is known as the equilibrium constant expression, and Kc or Keq is called the equilibrium constant. Now, before we talk about a reaction here, I want to talk about some different types of Ks, all right? And like I said, there are more than one different types of Ks, right? First one, like we talked about this one, for Kc or Keq, all right? Kc or Keq. This is the general one. For Kc or Keq, you'll know here that we use concentration, all right? Normally, Kc or Keq is used with substances that are in solution, but they don't necessarily have to be, all right? So normally, this involves solutions, all right? You can think, double replacement reactions. We have reactants and potentially products in solution. Combo and decomp, that could be a possibility. Combustion, no. So this one, we normally wouldn't see this with that. And so we use molarity as our unit. All right, we use molarity, okay, concentrations. All right, we have a Kp. Anybody have a guess as to what Kp means? Well, if you guess pressure, you're right. All right, so this is an equilibrium constant that is normally used in reactions that involve only gases. All right, only gases. Again, could be a combo or decomp. It's definitely possible. Not going to involve double replacement. Probably not going to involve single replacement. Although you can have a gas there, most of the time you're dealing with solutions and or solids. So now combustion reactions a lot of time involve only gases. So you'll see Kp used quite a bit with combustion reactions. So this normally involves reactions involving gases, and our unit of measure then is usually, of course, ATM or kPAs. Okay. ATM or KPAs. We have what is called KSP. Anybody have a guess as to what that might stand for? That's a little tougher one. KSP actually, the SP actually stands for solubility product. SP, solubility product. So basically, we're dealing with reactions involving solubility. So in all likelihood, we're probably dealing with a double replacement reaction. All right, that doesn't necessarily have to be, but in regards to solubility, that's usually the type of reaction we're looking at, precipitation reaction. And so again, these normally involve reactions where we have our reactants in solution. And so once again, we use molarity or molar concentration as our unit. And again, this specifically involves solubility. Solubility. And then another one, we have Ka. Hopefully you can see that down there. We have Ka and we have Kb. All right. If you can't see that, by the way, I'm sorry, but you should have, remember, you have available to you a note packet where my notes are filled out on there, so you can refer to that. This also, again, solutions. So we're dealing with reactants that are in solution. However, if you might think about A and B, what have we talked about recently that A and B? Well, if you guessed acids and bases, you're right. All right. So here again, these are constants, equilibrium constants specific to acid-base reactions. All right. So again, we're using concentration and molarity, but now we're dealing with acids and bases. Acids and bases. There are a few other Ks. These are mainly the ones you would ever see, all right? Whether it be in AP or in college or both. Kc or Keq, again, is the general equilibrium constant. Kp is for just gases. Ksp is for solubility. And Ka and Kb are for acids and bases. All right, so now let's look at this right here, which talks about the general equilibrium constant, C or K and Q. So here we have a reaction at equilibrium. So again, it's got to be in a system. We have N2O4 gas in equilibrium with 2NO2 gas. And so the equilibrium constant expression, or K, for products over reactants. And Kc or Keq uses concentration. So this is the concentration of our product, which is NO2, raised to the second power because of that mole number 2 right there. Over the concentration of N2O4, our reactant. And again, there's just a 1 there. And so just like there's a 1 there, there would be a 1 there as well. But since it's a 1, we don't need it. So this will be the equilibrium expression for this reaction. Now, based on what those concentrations are at a given set of conditions in a closed system, we would plug those in here and get a value for K. Okay, and we will do that here shortly. Maybe not today, but soon. All right. So let's go to the next page. So Kc, get this out of the way here. Kc or Keq can be determined experimentally by analyzing the equilibrium concentrations of N2O4 and NO2. We're working with the same reaction here. In fact, I'll write it up here again. So we had N2O4 gas in equilibrium with 2NO2 gas. And again, our Kc or Keq for this reaction, products over reactants, concentration of NO2 squared over concentration of N2O4. So here's our equilibrium reaction. Here's our equilibrium expression. So we analyze the concentrations at equilibrium of these two substances in which different initial concentrations of each were used. So if you notice here, we did 4 experiments. In experiment 1, we started out with NO2 only in the container. That's it. No N2O4. in experiment 2, we again started out with NO2 only, no N2O4, but a different concentration now. Third one, same thing, different concentration of NO2, no N2O4. And in the last experiment 4, we actually started with N2O4, no NO2 at all, and at a specific concentration. We then allowed the reaction to come to equilibrium where the forward rate and the reverse rate were the same. And we measured the concentrations at equilibrium. And as you can see here, they vary somewhat, except for this one. Wonder why? Well, let's see why. So here we have our equilibrium concentration of N2O4. Here we have our equilibrium concentration of NO2 for each of the 4 experiments. And it is these two numbers, the equilibrium values, that go in the K expression, whereby we can solve for K. So let's just, as an example, let's do for experiment 1. So for experiment 1, Kc would be, here's our Kc expression right here. So NO2 is 0.0172 squared, and N2O4 goes on the bottom, 0.00140. So if we square this, divide by this, and take it out, looks like 3 sig figs, we get a value of K of 0.211. Okay? So in experiment 2, we started with a different concentration of NO2, allowed them to come to equilibrium, and here's our numbers now. So for experiment 2, Kc is NO2 squared, 0.0243 squared over 0.00280. Guess what's going to happen? Anybody guess? If you guess you get the same number, you're right. You do. This is what equilibrium means, all right? This is what equilibrium means. Once equilibrium is achieved and the rates of the forward and the reverse reaction are the same, that value of K is exactly what it says it is. Equilibrium constant, right? It is a constant. If we did the same thing for these, did the same thing. Products over reactants. The product squared over the reactant in the case of this reaction. The values you get for K within rounding reason, of course, because the precision of these, of course, is not exact. You're going to get a value very, very close, if not the same, to 0.211. Okay? So Kc can be calculated using the equilibrium concentrations. Again, that's what you must use, not the initial ones, the equilibrium ones, of the two substances from any of the experiments, and the same value is obtained each time within reasonable limits of error, of course. And so what we did here, we showed that, I think if we use, experiment. So if we took the data of experiment 3, so experiment 3, we started with 0.400 of NO2, and experiment 4, we didn't start with any. So we started up here and down here. And yet, at equilibrium, which is out here after time, and equilibrium, we both have the same value K, right? So this one works its way this way, this one works its way this way, but you end up at the same value of K, all right? The ratio of product to reactant, regardless of how you started, at equilibrium is the same value. And in this case, K was approximately 0.211. Okay. Now, concentrations are being compared in both the numerator and denominator. All right. This similarity, and so is this. All right. Then the equilibrium constant technically does not have a unit. All right. It is dimensionless. All right. So K does not require a unit, kind of like pH, all right? No unit K. For the equilibrium constant K, that is. All right? All right, let's go to the next page. The equilibrium constant for pressure. Okay, I mentioned this, Kp. When the, whoops, get out of the way. When the reactants and products are gases, all right, the equilibrium constant expression can be formulated in terms of the partial pressures of the gases involved in the reaction rather than molar concentration. We've talked about this before. I mean, when you're dealing with gases, it's much easier quantitatively to use pressures than it is concentration. Although we do have a relationship between the two, which we'll get to in our next lesson of gas law. But in general, when our reactants and products are all gases, it's just easier. I should say it's more convenient to measure their pressures than it is their concentration, and so we can use those pressure values as a basis for calculating K. Only now, instead of calling it Kc or Kq, we call it Kp. All right. So here we have the same general setup that we did previously, only now all of our reactants and products are in gases, are in the gas phase. So the equilibrium condition now is expressed by this. It's still products over reactants, right? It's still products raised to the power of their mole coefficient over reactants, same thing. Only now, rather than concentrations, we're now using pressures, all right? So notice we don't have the brackets here because remember that bracket means molarity, all right? And molarity. We're not, so we use brackets with Kp, we just put our pressures in parentheses. Other than that, it's the same exact setup, all right? Products or reactants, okay? So we are going to stop right there. And I want to briefly go to the first assignment, all right, that it goes along with this lesson. Okay, so this assignment was entitled Laws Review and Equilibrium. All right, now, the first couple of problems were a review of rate laws. Good practice there. Need to know all that stuff. So I'm going to jump ahead past the rate law stuff. Here, beginning with number 4, involves some terminology that we talked about in regards to equilibrium and a closed system. On the next page, or I should say the last page, here we have two equilibrium constants that we talked about in our lesson today. The first one involved concentration, which was Kc or Kq. The second one, which was pressure, of course, was Kp. Now, remember, in Kc or Aq, we use concentration to measure, to express that. Okay, and so that concentration is measured in, all right, molarity. And then if we're going Kp, then we use a pressure measurement. Normally it's atmospheres, but it certainly could be Kp. Okay. Explain the equilibrium conditions of both reactants and products when the magnitude of K is large. Okay, so think about that. So for a general K, remember it's products over reactants. So whether it's concentration and molarity, if it's Kc or Kaq, or if it's pressure or Kp, it really doesn't matter. Let's just look at this in general. So it's a ratio of products to reactants. If K is big, I mean, what does that mean? This number over this one. It's a ratio. It's a fraction. All right. If K is big, then that means the numerator has got to be bigger, much bigger than the denominator. All right. So that means this value up here has got to be much larger than this one down here. What does that mean? Well, look, it means that at equilibrium, you have more products than you do reactants, which means what we say then is that the products are favored, okay? Or we say that the reaction favors the right side or the product side. If K is small, right? If this number here is small, then it means the denominator, which in this case is the reactants, has to be a larger value, a much larger value than the products. All right? So what does that mean? Well, if this number here is bigger than this number up here, if K has got a small value, then that means the concentration or pressures, as the case may be, of the reactant equilibrium is larger than the products. We say that equilibrium favors the left side or the reactant side, or we say that the reactants are favored. So that's what that means right there. Now I want to look at number 11. This is kind of a little common problem here. It asks us to write both. I want to look at letter with you. It asks you to write both Kc and Kp expressions for the following equilibrium reaction. First thing you got to do is balance the equation. All right, always. So let's see. Okay, we've got 5 there. So we need a 5 here, which then makes that 2 and makes that 2. All right. So if we're going to write the Kc expression, Kc involves concentration, all right? So that would mean, here's our product. We would have the concentration of N2O5 squared, because of that 2 right there, over the concentration of N2 squared times the concentration of O2 to the 5th power, all right? Products over reactants, since it's Kc, we use concentration. It also wants us to write Kp, all right, for the same reaction. Now, this is one we probably use normally because these are all gases. But like I said, you don't have to. So instead of concentrations now, we're going to use pressures. Otherwise, it's the same setup. So we have the pressure of N2O5. I just have that in parentheses now. Remember, brackets means concentration, so we don't use brackets there. It's still squared over the pressure of N2 squared times the pressure of O2 to the 5th power. Okay, so it's basically the same setup. Only here we would be using pressure measurements, probably in ATMs. Here we would be using concentration measurements in molarity. All right. So the values of K, given that these units and numbers are different, are going to be different. Now, but there again, here you're referring to K in regards to concentration. Here you're referring to K in regards to pressure. So the two values of K don't have to be the same, although I will say they could be. They could be, and I'll talk about that in our next lesson. So that ends the first lesson over equilibrium in general, what it means, how it's determined, what an equilibrium expression is, what a K is, and so on and so forth. So that concludes our first lesson in equilibrium, Unit 12.2. We will continue on with this in our next one. Take care, everybody, and I will talk to you again soon. See you guys. Take care.